Hello, everybody. Today, my name is Rodrigo Rezende. I'm professor from the postgraduate program in biotechnology from the University of Araraquara, São Paulo, Brazil. And today, we'll have the lecture entitled Additive Manufacturing in Tissue Engineering. This lecture will be ministered by Professor Paulo Bartolo, who I have the satisfaction to bring to you here today. Professor Paulo Bartolo is chair professor on advanced manufacturing at the School of Mechanical, Aerospace and Civil Engineering, MACE, from the University of Manchester, United Kingdom. Visiting professor at Nanyang University in Singapore, besides collaborator professor in universities in Mexico, Cuba, and Portugal. Dr. Bartolo holds a PhD degree in polymer physics from the University of Reading, a Master of Science in Mechanical Engineering, and a Licenciatura in Mechanical Engineering, both from the Technical University of Lisbon in Portugal. At the School of MACE, he is the head of the manufacturing group. At the University of Manchester, is the Industry 4.0 academic lead, member of the management board of the EPSRC and MRC Center for Doctoral Training in Regenerative Medicine, and team leader of the Industry 4.0 Society Challenge area within the digital futures. So it's a great satisfaction to have you here this day, Professor Paulo Bartolo, who's a big friend and especially was my advisor during my PhD in Portugal. So thank you again for being here today, Paulo.
Thank you very much, Rodrigo, and thanks for your kind introduction, and also for the invitation, which I gladly accept. It's an honor to be part of the first digital conference on 3D biofabrication and bioprinting. It's always a pleasure to participate in conferences in Brazil, especially organized by good friends. For those who don't know where is Manchester, let me tell you that Manchester is a third of the UK, halfway between London and Edinburgh. It's a highly industrialized area, but also surrounded by very beautiful places like the Lake District and the Peak District. It is also the home of the University of Manchester, which is the largest single campus university in the UK, quite close to the city center. For a top university, rankings are always important. So the University of Manchester is currently the number 27 in the world. It's also the first university in Europe in terms of social and environmental impact, and the third in the world. And it has been the home of 25 Nobel Prize winners, and the majority of our research is considered as world leading or international excellent. You already mentioned that, but let me recap. So I have multiple roles at university. I'm leading the Industry 4.0 initiative, which is about the use of digital tools and technologies, advanced materials, data, and automation for sustainable and smart products, services, and organizations. We have a different perspective of the Industry 4.0. So for us, it's not only a technical transformation, but also a complex social and technical transformation of the world. And as part of these roles, I'm coordinating the activities of a large number of academics from different faculties across the university, and these activities act also as the interface between the university and external world, regional government partners, industrial partners, and funders. I'm also the head of the manufacturing group, a group of academics doing research around three main domains: innovative manufacturing process, smart manufacturing systems, and digital manufacturing, enabled by key technologies. And these key technologies are for us laser-based additive manufacturing, multi-scale manufacturing, mechatronics, and molding and simulation, addressing relevant economic, social, and environmental challenges. And finally, I'm leading a group of 50 members, academics, fellows and postdoctoral researchers, PhD students, and MSc students, focusing on biofabrication and medical engineering broadly, doing research in terms of advanced materials, mostly degradable materials, but also some research activities around non-degradable materials, using a wide range of additive manufacturing, but also non-additive and hybrid technologies, focusing on design issues, simulation issues, for a wide range of applications such as bone, cartilage, nerve, muscle, or skin regeneration. In all of these duties, additive manufacturing is the core technology. And in Manchester, we have machines corresponding to all the main additive manufacturing principles commercially available. But we are also developing our own machines, targeting specific applications, addressing some limitations identified in commercial available ones. And one example is this hybrid machine that we developed, comprising a multi-extrusion system and a multi-jet plasma system. And using this machine, it is possible to print multiple materials per layer, and to use this multi-jet system to do surface modifications per layer also in a controlled way. And this is the ideal machine to create functional graded structures. And we published a couple of papers describing the equipment and also some applications using heat. Another machine that we are developing is the concept of electrochemical additive manufacturing. This is to print shape memory materials and to support our 4D printing activities, which is a highly important piece of work in my group. Throughout my multiple roles, we are using additive manufacturing for multiple applications, for aerospace applications, for the tooling industry. Additive manufacturing in construction is highly relevant, and more recently also to develop biosensors. And to support all of these activities, we are also designing new nozzles, allowing us to manipulate with different materials using screw or pressure to create functional graded filaments, or for example, novel pultrusion, compression, coaxial nozzles with expanding chambers to create much more complex filaments. I told you that we are exploring these two different applications, and one is, and this is relatively new in my group, is to produce biosensors. And one example is a project that we have funded by Bill and Melinda Gates Foundation, where the aim is to develop a biosensor to detect the presence of yellow rust. This is a very relevant problem, especially in the North Africa, because the yellow rust is responsible for the lose-up of 25% of the global wheat yield. And it's very difficult to detect. Can be visually detected after 14 days of infection, but at this stage, no countermeasures can be taken. So within this project, we are, first of all, trying to mimic the structure of the leaf. At the bottom of this slide, I have a scanning electron microscopy image and an optical image showing the surface of a leaf, showing also the micro grooves that characterize the leaf, and also these circular structures which corresponds to vertical channels in the leaf called stomata. And it's through these stomata channels that the pathogens penetrates deeper in the plant. These stomata are opening and closing depending on the environmental conditions, mainly temperature, humidity. So we are trying to mimic this by developing a multi-layer biosensor. The first layer must have these morphing capabilities, so the ability to open these channels and close the channels depending on the environmental conditions, and also the ability to provide the necessary support for the germination of the pathogens. And then we'll have a sensing layer, basically formed by an hydrogel containing sucrose that will detect the pathogen due to the production of glucose, which induces a color change that is detected by a camera. I have a movie to illustrate the concept. This was extracted from a program broadcasted last year by BBC, highlighting the use of IT technologies and advanced materials and advanced technologies for agricultural applications, and they highlighted our project.
Z-spore. It enters a sensor biologically engineered to mimic the crop. Like a kind of fire alarm, the sensor sets off an early alert. They can all be linked up, warning other farmers weeks before any damage is visible. And they can be 3D printed.
More recently, we started also a collaboration with colleagues from the Department of Materials at the University of Manchester, and also with colleagues from Chapman University in the United States, focusing on the development of pH responsive nano and microgels, and we published a couple of papers around this work. In terms of tissue engineering, which is the core of my talk today, we are exploring additive manufacturing for two main approaches. One is the so-called scaffold-based approach. So we are using different materials and different additive manufacturing technologies to produce these three-dimensional porous structures. And the second one, we are using different types of additive manufacturing to print biowings. This is the so-called bioprinting approach, allowing us to create cell-laden constructs. And this is quite interesting because it's an approach that allows us to think about strategies to print these materials directly into the body. We are exploring this for skin and for cartilage. Cartilage is relatively recent in the group. But in terms of skin, we started a long time ago a project focusing on in-situ skin printing. This comprises a machine and the biowings. A machine is a normal mechanical engineering machine, a machine that comprises a scanning device to scan the body of the patient, determining the extension of the lesions. And then this information is used to control another printing system that prints different biowings to create a synthetic and artificial skin. We investigated a wide range of materials as potential biowings, but in the last 3 years we focus on pectin. And we focus on pectin for a couple of reasons. First, it's not a commonly used material. It is an hydrophilic and biocompatible material with gelling capabilities, exudate absorption properties, but presenting a lack of biochemical cues, which for us is an advantage because it means that we can tailor, we can decorate pectin according to our needs. We focus also on a photo-curable additive manufacturing approach. So first of all, it was necessary to functionalize pectin. We have done that using methacrylate anhydride, and we consider different levels of functionalization, different levels of methacrylation to create pre-polymers with different rheomechanical properties. And then we prepare a protocol to print this bio-ink. So the pectin was decorated with RGDs, encapsulated human ectothermal fibroblasts. We had calcium chloride into the polymer solution to slightly increase the viscosity through an ionic cross-linking to guarantee a good printability of the bio-ink. And then the bio-ink is printed and finally cross-linked through an UV curing reaction. The amount of calcium chloride was investigated and optimized regarding the flow properties of our material. And we explore also different types of photoinitiators, and the amount of photoinitiator was also optimized regarding the curing kinetics and also the biomechanical properties of the final gel. Preliminary results show that after 14 days post-printing, cells were live, creating cell networks, and also able to produce their own extracellular matrix. But we were not totally happy with the chemistry. So metacrylate polymerization is chain-grow polymerization process, inhibited by oxygen, creating non-homogeneous networks, characterized also by relatively slow reaction rates. So we decided to investigate a different chemistry. We focus on thiolene polymerization, which is a step-grow polymerization process, more efficient, faster, and also not inhibited by oxygen. And again, we decorated pectin with RGDs and also with MMPs, allowing us to gradually increase the free volume available to accommodate the cell spreading process. And then we start testing the best way to create the artificial skin, and the strategy is illustrated in this slide. So first, we print the pectin with fibroblasts. After that, we submerge the printed material in culture media during 7 days. And then we print the bio-ink containing keratinocytes, and again submerge the material in culture media during 7 days. And after that, we expose the upper layers to air, creating an air-liquid interface to induce stratification. And we obtain, using this approach, an artificial skin with high similarities with the human skin, not only in terms of its organization, in terms of the shape and organization of the cells in the different layers, thickness of the layers. We are currently increasing the complexity of our approach, adding other types of cells. I have also 2 PhD students that are focusing on this approach, but to create a skin equivalent to study melanoma. This means that we need to change again the chemistry, because we are no longer using a UV curing approach. We need to change the photoinitiators being used, and we are also changing to a different aerogel. But also for skin, we are using other technologies rather than additive manufacturing to produce wound dressings. We reported the first work few years ago using polyvinyl alcohol membranes with umbilical cord cells to treat significant large skin lesions in animals. And we have a strong partnership also with a company in UK, Matoka Holdings, where we are using electrospinning to create wound dressings made with specific biocompatible and biodegradable materials, incorporating materials that are being developed in partnership with Matoka, with antiviral and antibacterial properties. It's a kind of a synthetic RNA being developed and incorporated in these wound dressings, and we had a couple of patents together with Matoka. Now, in terms of the scaffold-based approach, bone is probably the best example of our work. Here we are exploring different materials, also different technologies, mainly extrusion-based and screw extrusion-based additive manufacturing, but also hybrid systems combining extrusion and electrospinning, investigating the performance of these scaffolds both in vitro and in vivo, and also trying to develop surface modification approaches to improve the properties of the produced scaffolds. Today, I'm not going to provide too much detail about these different materials and the effect of these different materials. I'm focusing more on recent works related to surface modification, the concept of hierarchical scaffolds. So in terms of surface modification, we published this year one paper showing a strategy where the scaffolds were submitted to an acetone vapor annealing process to induce the formation of microporosity on the filaments of the scaffold. Through this method, free amorphous regions are delocalized from the surface of the filaments and recrystallize on pre-existing crystalline zones, inducing the formation of a hierarchical nanostructure on the filaments. The scaffolds were then submitted to, were then doped with dopamine to increase not only the hydrophilicity of the scaffolds, but also cell adhesion and cell spreading. So this here, we presented another method. In this case, the previous one was tested with polycaprolactone scaffolds produced using an extrusion-based machine. In this case, we use structures produced using electrospinning and PLLA. The structures were coated with silica nanoparticles, and the reason for using silica nanoparticles was due to the high surface ratio of the silica nanoparticles and also the biocompatibility of these particles. This coating mechanism increased the strength of the construct and also the hydrophilicity, and the structures were also doped with dopamine, not only to increase the cell adhesion and spreading, but also the strength of the silica nanoparticles on the silica nanoparticles. And as I mentioned, in all cases, so the PLLA meshes and the treated meshes were able to support cell adhesion and proliferation, but much better results were observed with the structures modified with this method. We are exploring other technologies. So a few years ago, we reported the use of NOH to treat the scaffolds without compromising the mechanical properties. And our initial results show a positive effect on the osteogenic differentiation. This year, we published another paper showing also a positive effect on chondrogenesis. And another strategy was based on coating the scaffolds with P1 protein, extracted from latex from the rubber tree in Brazil. This is a project funded by FAPESP and University of Manchester, and we obtained very interesting results using this protein, not only in terms of improving cell adhesion, but also the osteogenic differentiation and also angiogenesis. Another area particularly relevant for us is the design and fabrication of hierarchical scaffolds. We published a paper this year showing this approach using an extrusion-based process to create PCl hydroxyapatite and multi-wall carbon nanotube scaffolds, mimicking the micro and nanoscale structure of bone. In this paper, we showed that the multi-wall carbon nanotubes were aligned along the printing direction, similar to the collagen fibrils in the bone, with nano hydroxyapatite particles interdispersed between the multi-wall carbon nanotubes, acting as the natural hydroxyapatite crystals in bone. Transvision electron microscopy and polarized Raman prove that the multi-wall carbon nanotubes were aligned along the printing direction, and also the presence of the nano hydroxyapatite particles interdispersed around the multi-wall carbon nanotubes. The addition of the multi-wall carbon nanotubes had a positive impact, enhancing the osteogenic differentiation, and also increasing alkaline phosphatase, collagen, and osteocalcine expressions. But nevertheless, we need to do further research to determine the best ratio between multi-wall carbon nanotubes and hydroxyapatite to improve not only the physicochemical properties of the scaffold, but also the cell response. We're also designing and producing hierarchical scaffolds through a combination of multiple techniques. Again, this year, we published a paper in 3D printing and additive manufacturing. It was also highlighted in the cover, where we created dual-scale scaffolds using a setup combining extrusion additive manufacturing with non-rotational electrospinning. And more recently, we published another paper in additive manufacturing where we describe a different setup, again using extrusion-based process, but also a rotational electrospinning system. And the results show that by optimizing the processing conditions, it was possible to obtain high mass density with highly aligned fibers embedded in the scaffold. We controlled the alignment of the fibers by increasing the velocity of the rotational velocity in the electrospinning system, and by increasing the alignment of the fibers, we increase the cell anisotropy and a more organized cytoskeleton. Bone is, as you know, piezoelectric properties and also reverse piezoelectric properties. So we are also focusing on the concepts of electroactive scaffolds and piezoelectric scaffolds to enhance both osteogenesis and angiogenesis. An example is the work that we are doing. This is also in partnership with a couple of colleagues and colleagues in Brazil, colleagues in Araras. And in this case, we explore the use of electroactive scaffolds and electrical stimulation to regenerate critical size bone defects created in the calvario of rats. And we consider different routes. So one is the natural regeneration route, which was the reference for us with and without electrical stimulation. In the second case, we filled the defect with polycaprolactone scaffolds, again with and without electrical stimulation. And finally, we filled the defect with electroactive scaffolds, PCl scaffolds containing relatively small amounts of graphene, around 1%, and again with and without electrical stimulation. The photomicrography images of the defect are presented in these slides, and the results show that in the control case, so the natural bone regeneration, it was possible to observe the formation of a thin connective tissue, and in the case of applying electrical stimulation, the presence of pockets of new bone at the edges of the defect, across the edges of the defect. In the case of PCl scaffolds with and without electrical stimulation, we observe the formation of a connective tissue around the filaments of the scaffold, and also islands of new bone embedded in this connective tissue. And by applying electrical stimulation, we observe a much more organized new bone being formed. In the case of electroactive scaffolds, with and without electrical stimulation, we observe much higher levels of new bone and also much more organized. And this was also confirmed with photomicrography images, in this case stained with masonry coal. In this case, the blue dye identifies the connective tissue and also primary mineralized bone, depending on the intensity of the color, while the red dye corresponds to mineralized bone. So again, the results show that in the case of electroactive scaffolds with electrical stimulation, the amount of new bone formed is higher and the bone is much more organized. The small tiny black dots in the PCl graphene scaffolds corresponds to graphene, and these blue-red zones, this mix of blue and red zones, corresponds to tissue maturation. Recent results, in this case using different materials, using multiple carbon nanotubes, demonstrates what we observed before. So a very positive impact in terms of bone regeneration, also on the angiogenesis process. We're also pushing our research to close to the market, and a good example is a very large project that I'm coordinating called Bone Bricks. We designed this project 3 to 4 years ago when I visited Turkey, and I was impressed with the problem that Turkey was facing with the Syrian refugees displaced to Turkey. So Turkey hosts around 4 million Syrian refugees, and on their time, half of them were requiring medical treatment. Among these 2 million, 70% of them presented musculoskeletal problems. 47 presenting open fractures and very complex fractures, and around 100,000 people were affected by large bone defects. And the only solution the doctors had was amputation. So we decided to develop a strategy to address this problem. We approached a university in Turkey, Sabancı University, and also colleagues from the University of Portsmouth. Also a couple of clinicians at the Central Manchester University Hospitals, but also at the Kocaeli Training Medical University Hospital in Turkey, and also a couple of non-governmental organizations like the Syrian Relief, the Syrian British Medical Society, MAG, and others, to develop this project. And this project is the bone bricks. And the aim of the project is to develop and implement a patient-specific prosthetic to fill the bone loss due to injury, using a combination of biodegradable and biocompatible modular pieces, the so-called bone bricks, from a palette of shapes and sizes that fit together in a Lego-like way to form the prostheses. So once assembled, they create an hollow prosthesis, and this internal structure, this internal hollow cage, is filled with calcium sulfate paste containing antibiotics. We have a commercial partner which will be responsible for the commercial exploitation of the technology being generated. We are developing a couple of software tools, because the generation of the right type of shapes and sizes of these bone bricks is performed in an automatic way. We are also developing the software tools to send the information to the printing machines to print these different shapes, which are being easily assembled by the clinician. And for the first time, we are designing scaffolds, so our bone bricks, according to anatomical data. We are also investigating different types of printing strategies, creating structures with a gradient of porosity. Unfortunately, due to the COVID-19 pandemic, we delayed the animal tests to the beginning of October, and then the aim is also to run ethically approved human trials in Turkey with the support of TÜBİTAK. As I mentioned along this presentation, one of our aims is to design and develop structures with optimized properties. This is very complex because, for example, if you change the material preparation method, you change the rheological behavior of the material, and then we need to adjust the processing parameters. By changing the processing parameters, this has an impact on the scaffold design and an impact on the morphological development. And as a consequence, we are changing the chemical, physical, bio properties of the final scaffolds. So we need to understand and to establish models correlating all of these effects. And this is really complex. It's a multidimensional problem. We are starting doing this through a large number of synchrotron projects that we have been awarded, and we are performing studies in Oxford at the Diamond Center. 2 years ago, we published the first paper investigating the in-situ morphological development during the printing process. And since then, we keep developing models, allowing us, for example, to correlate the effect of processing conditions in terms of the crystalline structure, size of the crystalline structures, orientation of the crystalline structures, and the impact on the mechanical properties and also on the biological properties. The work was highlighted by many covers, and one of the papers was selected as one of the best papers published by macromolecular journals last year. But as I mentioned on the early beginning of my talk, within my group, we are not only focusing on the use of biodegradable materials. We are also using non-degradable materials. And I'm going to finish my talk with an example of it. It's a project related to the design and fabrication of the novel bone fixation plates. And the first problem that we target was the stress shielding problem, and consequently the bone loss issues associated with this stress shielding, which is due to the mechanical mismatch between the mechanical properties of the implant and the mechanical properties of bone. We solved this problem using topology optimization to redesign the shape of commercial available plates, printed using additive manufacturing technologies, in this case using titanium 64. Basically, topology optimization is used to remove materials from areas where the material is no longer needed and decrease the equivalent stiffness of the plates. We run topology optimization considering different loads and volume reductions, and as I mentioned, we use two different technologies, powder bed fusion technologies, but using different principles to print the fibers. One to print the plates. One was electron beam melting, and the other one was selective laser melting. The plates were, as I mentioned, optimized considering different loading conditions and different volume reductions. And by the end, it was possible to obtain a couple of new designs with properties in the cortical bone region. So we were very happy with these results. We also studied the plate cell interface and compared the results with commercial available plates. And again, the results were very, very positive, showing that without any post-processing operations, our plates were able to create a much better interface with cells than commercial available plates. So with this project, we solved the stress shielding problem. Now we are focusing on the second problem, which is related to the second surgery. So these are non-degradable plates, and there is no need to have the plate after the healing process. And besides that, there are some problems associated with keeping the plates in the body, related, for example, to the release of ions and the possible carcinogenic effect of those ion released. So what we are starting now is a similar approach. Use topology optimization to redesign these plates, but in this case, using a combination of biodegradable materials, polymers, ceramic materials, and also biodegradable metals, and then additive manufacturing to produce the optimal designed plates. And we are going to perform a completely different range of tests. One of our ideas is also to use these plates as drug delivery plates. So it is by knowing the degradation process and by controlling the degradation process, it will be possible to print at specific positions, for example, bisphosphonates that will be controlled released, designing these plates for osteoporotic bone applications. And with this, I complete my presentation. Again, it was a great pleasure to deliver this keynote. Unfortunately, it will be not possible be face to face to you, to ask your questions. But feel free to send me an email, to contact me by any other means. And I really hope to be able to return to Brazil soon, and who knows, maybe to participate in the second edition of this digital conference on 3D biofabrication and bioprinting. Thank you very much for your attention, and again, thank you very much, Rodrigo, for the invitation.
Thank you. Many thanks, Paulo. It's a very rich presentation. It's always good to see you presenting and showing all your results. And we can see a myriad of materials, techniques, devices, and other issues. It's very good to see how this technology has achieved even the social way, as you showed about this Syrian refugees project. It's very good. I would like to ask you a question. Since I watch you and know you since always 20 years, less a bit, and just recording, memorizing that you organize many VRAP conferences, 5 or 6 editions, if I'm not wrong. And I would like to ask you, have you seen this evolution of scaffolds since that time, 15 years ago, and how these processes involved are being progressed? How is the succeed of this scaffolds application? How have you seen this, Paulo?
Yeah. So it's interesting that you mentioned that we know each other for a long time, and if we return to let's say 15 years ago, I organized VRAP for the first time in 2003. On that time, the number of colleagues working on the use of additive manufacturing for medical applications was relatively small, and it was possible to know the names of everybody. Now it's totally impossible. So the number of researchers working in the area, it's incredibly high, and that's why the field is progressing so fast. One of these days, someone asked me, okay, what about examples of successful products? In fact, there are not too many. There are few companies selling these scaffolds. So there are some examples, but probably not too many as we could expect a few years ago. There is a big trend now related to bioprinting, and also few successful companies appearing and commercializing some bio inks. But it's important to pay attention to the scale. So additive manufacturing is now mentioned by everybody, and it's a relatively young technology. So additive manufacturing emerged 30 years ago, in the 1980s. The first time biofabrication was coined was in 2006 in an event organized by Veysun. Vladimir was there, and a couple of other colleagues. So we are talking about a very young domain. So I think that looking into the time scale, I think that the community achieved a lot, and probably in 10 years' time, we will see a totally different field.
Yes, and even considering all the IT technologies that have been growth and also evolved in this time. So, in considering images, treatment, simulations, and other issues that I didn't mention. And so, I think artificial intelligence, for example. So, I think all together.
People from computer science are also moving to the field, and I have no doubts that they will have a tremendous impact in the field. So in 5 years' time, we'll see a totally different domain. It's growing very fast.
Yes, and we get very happy and glad for that, because we're working on that, helping somehow, and we are here, and I hope we'll be there to see all these developments. That's
This reminds me also something that we created a long time ago. You were a key person. So on that time you were in Portugal, and you were a key person putting together the BioFab network. I don't remember if you remember it.
Yes.
But it was a big initiative exploiting the advantages that we have in South America, not only in terms of unique materials, but also unique expertise in molding, in additive manufacturing, in imaging. So one of these days we need to create a new BioFab network.
Yeah, I can't forget this. That's really a very important project for Brazil and Latin America, even also Portugal and Spain. Paulo, I'm sure that would be possible to keep talking here for many hours. It would be a pleasure. But by now, I have to finish this, and I'm sure that the audience would be very satisfied to hearing all your words. And I hope to have you here personally again soon after this pandemic time. Thank you again.
Thank you, Rodrigo, and I wish you all the best for the conference. I have no doubts that it will be a success.
Thank you, Paulo. Bye-bye.
Thank you. Bye. Bye-bye.